All right, so we're going to be starting Unit 5, Momentum. This encompasses Chapter 7 in your book, which is linear momentum and collisions. We're going to break this up into kind of two video segments. The first being momentum and impulse, and the second being conservation of momentum and collisions. So, what is momentum? So, momentum is the product of mass and velocity. So it can be simply thought about as inertia in motion. Okay? And it doesn't get any special unit of its own, so we think of it as kilograms for the mass and meters per second for the velocity. So it's kilogram meters per second. And it actually relates to Newton's first law, because if we think about Newton's first law was the idea of an object at rest, stayed at rest, an object in motion, stayed in motion in a straight line, basically. So it maintained this idea of linear kind of momentum, because it was mass, inertia, moving with velocity. So momentum is a vector quantity, and the momentum will point in the same direction as the velocity vector. And the reason we refer to this as linear momentum sometimes is there is another concept called angular or rotating momentum. We don't cover that in the honors level courses, but they do get into it in AP, just because you have more time during the AP course. So momentum is going to be, again, defined as mass times velocity, and the symbol we're going to use to represent momentum is a lowercase p. So P equals mv. Again, kilogram meters per second will be our unit. So you can think about a small object having a large velocity or a large object having a small velocity. They could possibly have the same momentum. So this little image here shows a girl throwing a large medicine ball kind of at a slower speed at a boy that's on a skateboard, and he goes back with a certain momentum. Or like a baseball-sized or a softball-sized object being thrown a lot faster at the boy on the skateboard gives the same momentum. So we've got two objects here. We have a beanbag bear and a rubber ball, each with the same mass, 1 kilogram. And they're going to fall downward with the same speed, we'll say 4 meters per second, before they hit the floor. And when we see them hit the floor, and the bear stops and the ball goes back upward. So the question is, what's the momentum change for each? Well, the beanbag bear has a P final of 0, because he goes from his mass times 0, equaling 0, minus an initial momentum of -4, because he had a mass and he was falling at -4. So 0 minus -4 is a change of 4 kilogram meters per second. The rubber ball bounces back up at 4, so its P final is the 1 kilogram times the 4 meters per second, or 4 kilogram meters per second. And it too had been falling at a -4 meters per second. So it has a -4 kilogram meters per second initial momentum. So when I do, again, final minus initial, I end up with 8 kilogram meters per second for the change in momentum of the rubber ball. So even though they both have the same initial momentums, because one stopped and then one bounced back up, they have different changes in momentum. And the idea of change in momentum is really, really important to us, because it's going to introduce this idea of impulse, because impulses cause changes in momentum. So an impulse is going to be the product of a force for a certain amount of time. So a small force acting over a long time, or a large force for a short time, could have the same impact, causing an impulse. We think about this for car crashes, right? You could either have, a car that goes from 0 to 60 very, very quickly, or a car that goes from 0 to 60 in a slightly longer time, and the forces are going to be dramatically different. Okay, that's why they design cars with crumple zones. That's why we, have things like airbags or seat belts, because we're trying to increase that stop time, right? Because the longer it takes the, human body to stop, or even the cars as a whole to stop, the lower the forces are on the passengers and the driver. So we use a capital J to represent impulse. And the units for impulse are the same as the units for momentum. So it's kilogram meters per second. And the impulse is a vector that points in the same direction as the force in this case. So when a force on an object changes its momentum, right, it's going to go from one direction to the other direction, or it could just stop it. This connects us actually back to Newton's second law because we're dealing with the idea of a force. So force is changing the motion of an object in some way. Well, if we notice here, this idea of change in momentum is like mass times a change in velocity, because generally our mass isn't changing, over a change in time. Well, if you look right there, isn't that our definition for acceleration? So mass times an acceleration, which was second law, so F equals ma. So the idea of a force changing the momentum of an object over time kind of makes sense based on Newton's second law. So again, force is either changing momentum over time, or the force times the change in time changes the momentum. These are our different definitions of impulse. So impulse is either force change in time, impulse is change in momentum, or you can think of, again, impulse as mass change in velocity. Right, so there's kind of three different ways to define impulse. So the momentum impulse theorem basically states that increasing the time over which a given impulse acts will decrease the average force. So this is why we design bicycle helmets, why packing material is designed the way it is, airbags, safety belts, crumple zones in cars, and cell phone cases, right? So when you have a bicycle helmet, you want to see that crack in the helmet if you fall off your bike. That meant it did its job. It deformed to protect your head. Packing materials, right? The little squishy packing peanuts, or the little airbaggy cushions of those inflated bags that they use now are designed to cushion any impacts, and increase the time that momentum change occurs over, so that the forces are smaller. In your cell phone cases, right? You don't want your phone to go from whatever it's falling at to zero in a quick time. You want it to go over a slower time, which is why the cases are designed, a little bit of a cushion to them, so they deform slightly and it doesn't crack your screen.